Think gravity is just the invisible glue keeping your feet on the ground? Think again. Everything you've ever been told about this mysterious force, from Newton's apple to why you don't float away, is probably dead wrong. The real truth, it's stranger than any sci-fi movie. Smash that like button if you're ready to have your mind blown, and hit subscribe right now, because we're about to unravel the universe's biggest lie. Scientists themselves can't even agree on what gravity really is. And by the end of this video, you'll see why this so-called simple force is the universe's biggest mystery. Let's dive in. Here's the thing. Nobody tells you about Isaac Newton and that famous apple. The whole story is a carefully crafted lie that Newton himself polished over decades to sound more dramatic than the messy reality of scientific discovery. Picture this. It's 1666. The plague is ripping through England. Universities are shut down, and a young Newton retreats to his family estate in Woolsthorpe Manor, not because he's some romantic genius seeking inspiration under fruit trees, but because he literally has nowhere else to go. Now, did an apple fall while he was sitting in the garden? Maybe, and historians actually think there's some truth to that part. But here's where the myth gets shredded. Newton didn't have some instantaneous eureka moment where the secrets of the universe suddenly downloaded into his brain, like he was plugging into the Matrix. That's Hollywood garbage, and it completely misrepresents how breakthroughs actually happen in science. What really went down was Newton watched an apple drop straight to the ground, not sideways, not at an angle, but directly toward the center of the earth. And that observation sparked a question in his mind. Why does the apple always fall perpendicular to the surface and never deviate from that path? He started wondering if the same force pulling the apple down could extend far beyond the treetops, maybe even as far as the moon, and whether that invisible pull could explain why the moon stays locked in orbit around Earth instead of flying off into space. But here's the kicker that destroys the legend. Newton didn't crack the full theory of universal gravitation until almost 20 years later, around 1685, when his colleague Edmund Halley asked him to calculate the forces responsible for elliptical planetary orbits. And that's when Newton finally put all the pieces together into the mathematical framework we know today. So the apple didn't give him gravity on a silver platter. It gave him a starting question. And then he spent 2 decades doing brutal calculations, questioning assumptions, and battling through mathematical dead ends before publishing his masterwork, the Principia Mathematica, which laid out the laws of motion and universal gravitation in a way that changed humanity's understanding of the cosmos forever. And get this, Newton himself didn't even write about the apple incident during his productive years. He only started telling the story when he was an old man in his 60s, decades after he'd already published his findings, almost like he was polishing his own mythology for posterity, which makes you wonder how much of the tale got exaggerated with each retelling. The Royal Society has manuscripts from Newton's friend William Stukely describing a conversation where Newton mentioned the apple, and Stukely wrote that Newton said, "Why should that apple always descend perpendicularly to the ground? Why should it not go sideways or upwards, but constantly to the Earth's center? Assuredly, the reason is that the Earth draws it, and there must be a drawing power in matter." Notice he's not saying, "I figured out gravity instantly." He's describing the beginning of a thought process, a curiosity that would take years to mature into a full theory. Now let's talk about what Newton actually discovered, because this is where things get wild and most people have zero clue about the real science. Newton's genius wasn't just realizing that gravity exists. Ancient philosophers knew things fall down, but he mathematically proved that the force of gravity between 2 objects depends on their masses and the distance between them. And here's the mind-blowing part. The force decreases with the square of the distance, which is called the inverse square law. And this single relationship unlocks the entire architecture of the solar system. Let me break it down in plain English. If you double the distance between 2 objects, the gravitational force doesn't just get cut in half, it becomes 1/4 as strong. Triple the distance, and the force drops to 1/9. Quadruple it, and you're down to 1/16. This isn't some minor detail. It's the mathematical skeleton key that explains why planets orbit the sun in ellipses, why the moon doesn't crash into Earth, and why you weigh slightly less on a mountaintop than at sea level, even though the difference is tiny. Newton's equation says the force equals the gravitational constant times the product of the two masses divided by the square of the distance between their centers. And when you plug real numbers into that formula, you can predict planetary motion with terrifying accuracy, which is exactly what Newton did. And it stunned the scientific world. But here's where it gets even stranger. Newton himself didn't know why gravity worked this way. He could describe it mathematically, but he had no clue what was actually causing this attractive force between masses. He famously wrote, "I have not been able to discover the cause of those properties of gravity from phenomena, and I frame no hypotheses," which is basically him saying, I can tell you how it works, but I have no idea why it exists, so I'm not going to make up explanations. That level of intellectual honesty was revolutionary, because earlier thinkers would have invented some philosophical hand-waving about invisible fluids or divine intervention. But Newton stuck to what he could prove with math and observations, even if it left gaping holes in his understanding. And people forget that Newton's contemporaries were skeptical. Some thought the idea of action at a distance, where two objects could affect each other without touching, was absurd, almost like magic, and they demanded a mechanical explanation that Newton couldn't provide. The inverse square law also reveals something unsettling. Gravity never stops, no matter how far apart objects are. The force gets weaker with distance, sure, but it never hits zero, which means technically, every single atom in your body is gravitationally attracted to every other atom in the universe, from the chair you're sitting on to distant galaxies billions of light years away. The pull from those faraway objects is so ridiculously weak that it's completely negligible in everyday life, like a billionth of a Newton. But it's still there, subtly tugging at you, connecting you to the entire cosmos in this invisible web of attraction that never switches off. That's both beautiful and kind of terrifying when you think about it. Now let's get to the part nobody explains in school. Newton's gravity model works astonishingly well for most situations. It got us to the moon, keeps GPS satellites in sync, and lets us predict eclipses centuries in advance. But it's not the full story, and Newton knew it had problems he couldn't solve. For instance, he couldn't explain why the orbit of Mercury was slightly off from what his equations predicted, and that tiny discrepancy haunted astronomers for centuries until Einstein came along and completely rewrote the rulebook. But before Einstein, Newton's inverse square law was the undisputed king of physics, and it still is for the vast majority of practical calculations, because even though Einstein's general relativity is technically more accurate, Newton's version is simpler and works perfectly for anything that doesn't involve extreme gravity or speeds approaching light. So engineers still use Newton's formulas for launching rockets and designing bridges. The real takeaway from the Apple myth is this: discovery isn't about magical moments of inspiration, where the universe just hands you the answer. It's about asking the right questions, doing the hard work of testing ideas against reality, and being willing to spend decades refining your theories until they actually match the data. Even when nobody believes you, and you don't understand the deeper why behind your own equations. Newton didn't discover gravity because an apple bonked him on the head. He discovered the mathematical language of gravity because he had the patience and obsession to chase a simple observation about falling fruit all the way to its logical conclusion through years of calculation and doubt, until he could describe the invisible force holding the solar system together with a single, elegant equation. And that's the story they should tell in schools, because it's way more inspiring than a fairy tale about instant genius, and it actually teaches you how science works, slowly, messily, and with a lot of sweat and frustration before you get anywhere close to a breakthrough. The apple didn't reveal the secrets of the universe. It just asked Newton a question he couldn't stop thinking about, and that relentless curiosity is what changed everything. Everything you learned about gravity from Newton is technically wrong, or at least wildly incomplete. And the scientist who shattered that centuries-old worldview wasn't some random upstart. It was Albert Einstein, who in 1915 published his general theory of relativity and completely rewrote the cosmic rulebook by declaring something absolutely insane. Gravity isn't actually a force at all, but rather the bending and warping of the very fabric of space and time itself, which means when you're standing on Earth, feeling the pull of gravity, you're not being yanked downward by some invisible tether. You're literally moving through curved space-time, and that curvature is what creates the sensation of weight. Let that sink in for a second, because it's bonkers. Newton thought gravity was a mysterious force that reached across empty space and pulled objects together instantly, like some cosmic magnet. And for over 200 years, that model worked so well that nobody seriously questioned it. But Einstein came along and said, actually, space and time aren't just an empty stage where physics happens. They're dynamic, flexible, and they get distorted by mass and energy. And that distortion is what we mistakenly call a gravitational force. The journey to this revelation started with Einstein's earlier breakthrough, the special theory of relativity from 1905, which proved that space and time aren't separate, independent entities. They're woven together into a single four-dimensional fabric called spacetime, where your position in space and your position in time are both just coordinates in this unified structure. And the kicker is that measurements of space and time depend on your relative motion, so two observers moving at different speeds will disagree about how much time has passed, or how long a distance is, yet they'll both agree on the structure of space-time itself. But special relativity had a glaring hole. It didn't account for gravity, and that bothered Einstein for nearly a decade as he wrestled with how to incorporate acceleration and gravitational effects into his framework. The breakthrough came when Einstein realized something profound called the equivalence principle, which states that the effects of gravity are completely indistinguishable from the effects of acceleration in a small enough region of space. Imagine you're in an elevator in deep space with no gravity, and someone starts accelerating the elevator upward at 9.8 meters per second squared. You'd feel yourself pressed to the floor with exactly the same sensation as standing on Earth. And there's literally no experiment you could do inside that elevator to tell whether you're accelerating through empty space or sitting still in a gravitational field, because the two situations are fundamentally identical. Einstein took this idea and ran with it to its mind-bending conclusion. If gravity and acceleration are equivalent, and acceleration involves changes in motion through space-time, then gravity must also be a consequence of the geometry of space-time itself, not some separate force acting on objects from a distance. To visualize this, physicists love using the rubber sheet analogy, where you imagine space-time as a stretched fabric and massive objects, like stars and planets, as heavy balls placed on that fabric. The balls create dips and curves in the sheet. And if you roll a smaller marble nearby, it doesn't travel in a straight line, but instead curves around the depression created by the heavier object, following the warped contours of the fabric. That's essentially what's happening in real space-time. The sun's enormous mass warps the space-time around it, creating a kind of curved valley, and Earth isn't being pulled toward the sun by a force. It's simply following the straightest possible path through that curved geometry, which we perceive as an elliptical orbit. And the crazy thing is that what looks curved to us from the outside is actually a straight line, called a geodesic, from the perspective of the object moving through space-time. Einstein's field equations, which are the mathematical heart of general relativity, describe exactly how mass and energy tell space-time how to curve, and how that curved space-time then tells objects how to move. And physicist John Archibald Wheeler summed it up perfectly when he said, "Matter tells space-time how to curve, and curved space-time tells matter how to move." which is one of the most elegant descriptions of a physical law ever written. Now here's where things get even weirder. On Earth, where gravity is relatively weak, and speeds are slow compared to the speed of light, almost all of the gravitational effects we experience come from the warping of time, not space. Yeah, you read that right. Time itself runs at different rates, depending on how deep you are in a gravitational field. So clocks on a mountaintop tick slightly faster than clocks at sea level, because they're in a weaker gravitational field and experiencing less space-time curvature. And this isn't some theoretical curiosity. GPS satellites orbiting Earth have to account for this time dilation effect, because their clocks run faster than clocks on the ground. And if engineers didn't correct for it, your GPS navigation would drift off by kilometers within a single day. The spatial warping of space-time becomes significant only in extreme conditions, like near black holes or neutron stars, where gravity is so intense that space itself gets stretched and compressed in observable ways, causing light to bend around massive objects in a phenomenon called gravitational lensing, where distant galaxies appear distorted or even multiply image because their light has traveled through regions of severely warped space-time. Einstein predicted this light-bending effect in his equations, and it was spectacularly confirmed in 1919 during a solar eclipse when astronomers measured the positions of stars near the Sun and found that their apparent locations had shifted by exactly the amount Einstein calculated because the Sun's mass was bending the starlight passing close to it. And when the results were announced, Einstein became an overnight celebrity, catapulted to global fame as newspapers around the world proclaimed that Newton's gravity had been overthrown. One of the most powerful confirmations of Einstein's theory came from solving a problem that had stumped astronomers for decades. The orbit of Mercury doesn't behave exactly as Newton's equations predict, with its closest point to the Sun, called the perihelion, shifting by about 43 arcseconds per century more than expected. And nobody could explain why. Until Einstein applied his field equations to Mercury's orbit and found that the extra precession was a natural consequence of the strong space-time curvature near the Sun caused by the spatial distortion terms in his equations that Newton's theory completely missed. This was a smoking gun, proving that general relativity wasn't just a philosophical rewrite of gravity, but a more accurate description of reality that made measurable predictions Newton couldn't account for. Einstein's theory also predicted something absolutely wild, called frame dragging, where a rotating massive object like Earth doesn't just curve space-time, it actually twists it, dragging the fabric of space and time around with it like a spinning ball in honey. And this effect was confirmed in 2004 by NASA's Gravity Probe B satellite, which carried ultra-precise gyroscopes into orbit and measured how their axes drifted over time due to Earth's rotation warping space-time, and the results matched Einstein's predictions to stunning accuracy. Perhaps the most revolutionary prediction of general relativity is the existence of gravitational waves, which are ripples in space-time itself, caused by violent cosmic events like colliding black holes or neutron stars. Einstein calculated that when massive objects accelerate, they send waves propagating outward through the fabric of space-time at the speed of light, stretching and compressing space as they pass. But he thought these waves would be too weak to ever detect because space-time is incredibly stiff and resists being warped. For decades, gravitational waves remained a theoretical curiosity, until February 2016, when the LIGO Observatory announced the first direct detection of gravitational waves from two black holes, spiraling into each other over 1 billion light-years away, and the signal they measured was a tiny distortion in space-time, less than 1,000th the diameter of a proton. But it was unmistakable, proving that space-time really does ripple and flex, like Einstein said, and opening up an entirely new way to observe the universe. Not through light, but through the vibrations of space-time itself. The difference between Newton's and Einstein's views of gravity isn't just academic. It fundamentally changes what gravity is. Newton saw it as a mysterious action at a distance force that somehow reaches across empty space instantaneously to pull objects together, which never sat well with physicists because it seemed magical. Whereas Einstein explained gravity as a local effect, where objects simply follow the curves in space-time created by nearby mass and energy, with no spooky action required. In Newton's universe, space-time is a flat, unchanging background stage where physics plays out. But in Einstein's universe, space-time is a dynamic actor in the drama, bending and flexing in response to matter and energy. And that curvature dictates how everything moves, from falling apples to orbiting planets, to light itself. Your weight on Earth isn't caused by the planet pulling you down. It's caused by the fact that Earth's mass curves space-time around it, and you're trying to move along a straight path through that curved geometry. But the ground is in the way, pushing up against you and creating the sensation of weight. So in a very real sense, gravity isn't a force pushing or pulling you. It's the resistance you feel when something prevents you from following your natural path through curved space-time. This realization is so radical that it took the scientific community years to fully accept it. And even today, general relativity remains one of the most counterintuitive theories in physics, because it violates every common sense notion we have about how the universe works. Space and time aren't rigid containers. They're flexible, stretchable, and warpable, and massive objects reshape the very arena in which they exist, creating the illusion of gravitational attraction when really they're just altering the geometry of reality itself. Einstein's equations also revealed that space-time curvature isn't static, it's dynamic, meaning the shape of space-time changes as objects move. So when you walk across a room, you're actually creating tiny ripples in space-time that propagate outward at light speed, though they're so minuscule that detecting them is impossible with current technology. The theory even predicts that time and space can be so severely warped near black holes that time effectively stops at the event horizon from an outside observer's perspective, and inside the black hole, the roles of space and time flip, so that moving forward in time becomes like moving inward in space, inevitably dragging you toward the singularity at the center, where space-time curvature becomes infinite and the equations break down. Despite its incredible successes, general relativity has a dirty secret. It's completely incompatible with quantum mechanics, the other pillar of modern physics that governs the behavior of atoms and subatomic particles. And nobody has figured out how to reconcile the smooth, continuous space-time of Einstein's theory with the discrete, probabilistic nature of quantum fields, which is why physicists are desperately searching for a theory of quantum gravity that can unify these two frameworks and explain what happens in extreme conditions, like the Big Bang or the cores of black holes, where both quantum effects and space-time curvature are important. But for now, general relativity reigns supreme in the realm of massive objects and cosmic scales, giving us a picture of gravity that's utterly alien to our everyday intuition, yet mathematically beautiful and experimentally verified to extraordinary precision. The next time you feel the pull of gravity, remember you're not being pulled down by a force. You're coasting through the warped landscape of space-time, following the curves carved by Earth's mass. And that invisible geometry is what pins you to the ground, shapes the orbits of planets, bends light around stars, and ripples through the universe when black holes collide, all because mass and energy have the power to reshape the very fabric of existence itself. Here's one of the biggest lies people believe about space. Astronauts float around the International Space Station because there's no gravity up there, or because gravity is so weak at that altitude that it barely affects them. And if you believe that, you've fallen for one of the most persistent misconceptions in all of science. The truth is that gravity at the ISS altitude, which orbits about 250 miles above Earth's surface, is only about 10% weaker than the gravity you feel standing on the ground right now. Which means if you could magically teleport to the ISS's location without any sideways motion, you'd plummet toward Earth almost as fast as if you jumped off a building. So the idea that astronauts float because gravity disappears in space is complete nonsense. The real reason astronauts appear weightless has nothing to do with gravity being absent, and everything to do with the fact that they're in continuous free fall, constantly plummeting toward Earth at the same rate as the space station itself, and because both the astronaut and the station are falling together with identical accelerations. There's no relative motion between them, which creates the sensation of floating, even though gravity is pulling relentlessly on both. To understand why this works, you need to grasp what an orbit actually is, and the best way to visualize it comes from Isaac Newton himself, who imagined a cannon on top of an impossibly tall mountain, firing cannonballs horizontally. If you fire the cannonball slowly, it arcs down and hits the ground nearby, because gravity pulls it downward while it's moving forward. But if you fire it faster, it travels farther before hitting the ground. And if you keep increasing the speed, eventually you reach a magic velocity, where the cannonball falls toward Earth at exactly the same rate that Earth's curved surface drops away beneath it. So the cannonball never actually hits the ground, but instead keeps falling around the planet in a closed loop. And that's an orbit. The International Space Station is doing precisely this, hurtling sideways at about 17,500 miles per hour, which is over 22 times the speed of sound. And at that velocity, for every mile it falls toward Earth, due to gravity, the planet's surface curves away by roughly the same amount. So the station continuously misses the ground, perpetually falling but never landing, and the astronauts inside are falling right along with it at the exact same rate, which is why they appear to hover in midair relative to the walls and equipment around them. This state is called microgravity, not zero gravity, because gravity is absolutely still there. It's just that everything in the station is in free fall, so you don't feel the floor pushing up against you like you do on Earth. And that lack of a support force is what creates the sensation of weightlessness. Let me make this crystal clear with a thought experiment. Imagine you're in an elevator, and the cables snap, sending you plummeting downward. During those terrifying few seconds before you hit the ground, you'd feel completely weightless inside the elevator, floating relative to the walls, and if you let go of your phone, it would hover next to you, because both you and the phone are accelerating downward at 9.8 meters per second squared due to Earth's gravity. So there's no relative motion between you and the phone, and that's exactly what astronauts experience, except their elevator is moving so fast sideways that it keeps missing the Earth and falling forever in a circle. The confusion about weightlessness comes from conflating two different concepts: the gravitational force acting on you, which is your weight in the physics sense, and the sensation of weight, which is actually the normal force from the ground or floor pushing up against you when you stand on a scale. You're not measuring gravity's pull directly. You're measuring how hard the scale has to push up to keep you from falling through it. And in orbit, there's no floor pushing up because everything is in free fall. So the scale would read 0, even though Earth's gravity is still yanking on you with nearly the same force as when you're on the surface. This is why NASA uses the term microgravity instead of zero gravity. It's more accurate because tiny residual forces do exist on the ISS, like atmospheric drag from the thin upper atmosphere, slight variations in Earth's gravitational field across the length of the station, and even the movement of astronauts pushing off walls. But these effects are minuscule compared to the 9.8 meters per second squared acceleration you experience on Earth's surface. So for practical purposes, astronauts feel weightless, even though they're still firmly in Earth's gravitational grip. One of the most mind-blowing aspects of this is that the ISS is constantly falling. Every single second of every day, it's dropping toward Earth, and if it ever stopped moving sideways, it would crash into the planet within minutes. So the station has to maintain its orbital velocity, with periodic boosts from rocket thrusts, to counteract the tiny but persistent drag from atmospheric molecules at that altitude. Because even at 250 miles up, there are enough stray atoms to gradually slow the station down. And without those corrections, it would spiral inward and burn up in the atmosphere. The feeling of weightlessness isn't unique to space. You can experience it right here on Earth, anytime you're in free fall, like when you jump off a diving board, ride a roller coaster over a hill, or take a ride in NASA's famous Vomit Comet, which is an airplane that flies in parabolic arcs, climbing steeply and then nosing over into a dive that matches the acceleration of gravity, giving passengers inside about 25 seconds of weightlessness during each parabola. And this is how astronauts train for space missions, experiencing the exact same sensation they'll have in orbit, without ever leaving Earth's atmosphere. Another massive misconception is that you escape Earth's gravity once you cross some magical boundary called space, like the Kármán line at 62 miles altitude, which is the internationally recognized edge of space. People imagine that once you cross that line, gravity switches off like flipping a light switch. But that's absurd, because gravity is an inverse square force that weakens gradually with distance, never dropping to zero no matter how far you go. So even at the moon's orbit, 240,000 miles away, Earth's gravity is still strong enough to influence its motion. And technically, Earth's gravitational influence extends infinitely in all directions, though it becomes vanishingly weak at vast distances. At the altitude of the ISS, gravity is about 90% as strong as on Earth's surface, which you can calculate using Newton's inverse square law. The station orbits at roughly 400 kilometers above the surface, and Earth's radius is about 6,371 kilometers. So the total distance from Earth's center to the ISS is 6,771 kilometers. And if you square the ratio of Earth's radius to that distance, you get about 0.89, meaning gravity at the ISS is 89% of surface gravity, which is way more than enough to pull you down hard if you weren't moving sideways at orbital velocity. The reason astronauts don't need to be moving at 17,000 miles per hour when they're standing on Earth is that the ground provides a support force that counteracts gravity, holding them up and preventing them from accelerating downward. But in orbit, there's no ground to provide that force. So the only way to avoid crashing into Earth is to move so fast sideways that you're constantly falling around the curve of the planet. And that critical speed depends on your altitude. Closer to Earth, you need to go faster because gravity is stronger and the orbital circumference is smaller. While farther out, you can go slower because gravity is weaker and the circumference is larger. The physics of orbital mechanics reveals something counterintuitive. If you want to catch up to a spacecraft ahead of you in the same orbit, you don't speed up. You actually slow down, which drops you into a lower orbit where you travel faster and cover less distance per lap, allowing you to close the gap, and then you speed up again to raise your orbit back to match the target. And this bizarre reality is a direct consequence of the interplay between gravity and orbital velocity, where moving faster paradoxically puts you in a higher, slower orbit. Astronauts on the ISS aren't just floating aimlessly. They're in a carefully maintained orbit that requires constant monitoring and adjustment, because factors like solar radiation pressure, gravitational tugs from the moon and sun, and atmospheric drag are constantly trying to alter the station's trajectory. So mission control regularly fires the station's thrusters to keep it in the desired orbit. And without these corrections, the orbit would decay over time, causing the station to gradually lose altitude until it plunged back into the thick atmosphere and burned up. The sensation of weightlessness profoundly affects the human body in ways that reveal just how much we're adapted to living under constant gravitational load. Without the need to support their own weight, astronauts' bones lose density at a rate of about 1 to 2% per month, because the body stops investing resources in maintaining structures that aren't being stressed. and their muscles atrophy for the same reason, which is why astronauts have to exercise for hours every day on specialized equipment to prevent their bodies from deteriorating. And even with rigorous exercise, they still experience significant bone and muscle loss during long missions. Your inner ear, which helps you sense orientation and balance on Earth, goes haywire in microgravity because it relies on gravity to tell your brain which way is up. So about half of all astronauts experience space adaptation syndrome, commonly called space sickness, during their first few days in orbit, with symptoms like nausea, disorientation, and vomiting, until their brains adapt to the new sensory environment, where there's no consistent down direction. Fluids in the body also behave differently in microgravity. Normally, gravity pulls blood and other fluids toward your feet, but in orbit, fluids redistribute more evenly throughout the body, causing astronauts' faces to puff up and their legs to thin out, giving them a characteristic puffy appearance that's sometimes called moon face. And this fluid shift can affect vision because increased pressure in the skull pushes on the backs of the eyeballs, causing changes in their shape that blur vision. And some astronauts experience permanent vision changes after long-duration missions, which is a major concern for future trips to Mars that could last years. Even simple tasks like eating and drinking become challenging in microgravity, because food and liquids don't settle in your stomach the way they do on Earth. They just float around inside you, and without gravity to separate gas from liquid in your stomach, burping becomes risky because you might accidentally expel liquid along with the gas. So astronauts learn to suppress burps or risk what they call a wet burp, which is exactly as unpleasant as it sounds. The misconception that there's no gravity in space probably stems from early science fiction and educational materials that oversimplified the concept, combined with the fact that weightlessness is an intuitive but misleading term. You're not weightless in the physics sense, because gravity is still acting on you with significant force. You're just in a state where nothing is pushing back against that force, so you accelerate freely along with everything around you. And that shared acceleration eliminates the relative forces that create the sensation of weight. To drive this home, consider what would happen if the ISS suddenly stopped moving sideways and just hung motionless in space. At that altitude, the astronauts would immediately feel the return of weight, as both they and the station began accelerating downward at about 8.8 meters per second squared, roughly 90% of Earth's surface gravity, and they'd have about 10 minutes of increasingly terrifying descent before the station hit the upper atmosphere and began burning up from friction with air molecules. The bottom line is that orbiting isn't about escaping gravity. It's about moving so fast sideways that you fall around the planet instead of into it, and astronauts float. Not because gravity has disappeared, but because they're in an endless controlled fall, where everything around them is falling at exactly the same rate, eliminating the normal forces that create the sensation of weight. And understanding this distinction is crucial, because it reveals that gravity's influence extends far beyond Earth's surface, shaping the motions of satellites, the moon, and even the paths of distant spacecraft, exploring the outer solar system, all of which are navigating through gravitational fields that never truly vanish, but merely weaken with distance. And that persistent, inescapable pull is what keeps the cosmic machinery running, from the smallest asteroid to the grandest galaxy. If you think gravity is powerful on Earth, buckle up, because in the most extreme corners of the universe, gravity becomes so outrageously intense that it rips the fabric of space-time itself, creating cosmic monsters called black holes that trap literally everything that ventures too close, including light, the fastest thing in existence. And when I say trap, I mean permanently, with zero chance of escape. Because once you cross a black hole's point of no return, not even moving at 300,000 kilometers per second, which is light speed, can save you from being dragged into oblivion. Black holes are what happens when gravity wins the ultimate cosmic battle. crushing matter down to such insane densities that the laws of physics as we understand them completely break down. And the whole concept seems so absurd that when Albert Einstein's equations first predicted their existence in 1915, even Einstein himself didn't believe they could actually be real, thinking they were just mathematical curiosities with no physical counterpart in nature. But he was wrong, spectacularly wrong, because black holes aren't just real. They're everywhere, lurking at the centers, says most galaxies, including our own Milky Way, where a supermassive black hole named Sagittarius A star, with a mass of about 4 million times our Sun, sits 26,000 light-years away, quietly devouring anything unlucky enough to wander into its gravitational death grip. The story of how black holes form reads like cosmic tragedy. Imagine a massive star, at least 10 to 20 times the Sun's mass, burning bright for millions of years by fusing hydrogen into helium in its core, with the outward pressure from this nuclear fusion perfectly balancing the inward crush of gravity, creating a stable equilibrium that keeps the star from collapsing. But all good things end, and when the star exhausts its nuclear fuel, first burning through hydrogen, then helium, then carbon and oxygen, climbing up the periodic table until it's creating iron in its core. Everything stops dead because iron fusion doesn't release energy. It consumes it. So suddenly there's no outward pressure to counteract gravity's relentless inward pull. And in a fraction of a second, the core implodes catastrophically, collapsing from something the size of Earth down to a sphere, maybe 20 kilometers across. And the outer layers rebound off this compressed core in a supernova explosion so violent it briefly outshines an entire galaxy, blasting stellar debris across light years while the core continues its gravitational death spiral. If the core's mass exceeds about 3 times the Sun's mass, which physicists call the Tolman-Oppenheimer-Volkoff limit, not even the quantum pressure from neutrons can halt the collapse, and the core crushes down past the point of no return, shrinking forever towards zero volume and infinite density, a mathematical nightmare called a singularity. And as it collapses, the gravitational field at its surface becomes so overwhelmingly strong that the escape velocity, which is the speed you'd need to break free, exceeds the speed of light. And since nothing can travel faster than light, nothing can escape, creating a region of space-time that's effectively cut off from the rest of the universe. The boundary marking this point of no return is called the event horizon, and it's not a physical surface or wall. It's more like an invisible membrane in space-time, beyond which all paths, no matter which direction you try to move, lead inexorably inward toward the singularity. And the radius of this horizon depends only on the black hole's mass, following a deceptively simple relationship called the Schwarzschild radius, where you take twice the gravitational constant times the mass and divide by the speed of light squared. And plugging in numbers reveals that to turn Earth into a black hole, you'd have to crush its entire mass down to a sphere with a radius of about 9 millimeters, roughly the size of a marble, while the Sun would need to be compressed to a radius of about 3 kilometers. And these absurd compressions show just how much empty space exists in normal matter, and how extreme gravity has to become before forming a black hole. Now here's where things get truly mind-bending. Light doesn't actually get pulled into black holes in the way you might imagine, because gravity doesn't pull on light directly through mass. Remember, photons have zero rest mass. Instead, massive objects curve space-time itself, and light travels along the shortest paths through that curved geometry, called geodesics. So when space-time near a black hole gets warped to extreme degrees, those geodesics bend dramatically, and at the event horizon, space-time curves so sharply that all geodesics, including the paths light would naturally follow, point inward, making escape geometrically impossible, regardless of how fast you're moving. You can visualize this by imagining space-time as a stretched rubber sheet, and the black hole as creating an infinitely steep pit in that sheet. Once you roll past the edge of the pit, there's no trajectory that leads back up and out. All paths spiral down to the center. And that's what happens to light at the event horizon, where the curvature becomes so severe that even traveling at maximum universal speed isn't enough to overcome it. There's a fascinating region just outside the event horizon called the photon sphere, located at 1.5 times the Schwarzschild radius for a non-rotating black hole, where light can actually orbit the black hole in an unstable circular path, neither falling in nor escaping. And if you could somehow position yourself there and look tangentially, you'd theoretically see the back of your own head, because light would complete a full orbit around the black hole before reaching your eyes. Though this orbit is so unstable that the slightest perturbation would send the photons either spiraling inward or shooting off into space. The name black hole was coined in 1967 by physicist John Wheeler, who needed a catchy term to replace the awkward gravitationally completely collapsed object, and the name stuck because it perfectly captures the essence of these objects. They're black because no light escapes them, appearing as absolute voids against the star-filled backdrop of space, and they're holes in the sense that anything falling in disappears from the observable universe forever, with no way to retrieve information about what's inside. Before matter crosses the event horizon, however, something spectacular happens. As gas, dust, or even entire stars spiral inward, they form what's called an accretion disk, a swirling maelstrom of superheated material that orbits the black hole at relativistic speeds, and the intense friction and gravitational compression heat this disk to millions of degrees, causing it to emit torrents of X-rays and other high-energy radiation, making the immediate vicinity of black holes some of the brightest objects in the universe. Even though the black holes themselves emit nothing, and these blazing accretion disks are how astronomers detect black holes by spotting the telltale X-ray signatures of matter being torn apart and heated to absurd temperatures moments before it vanishes behind the event horizon. Einstein's general relativity predicts something even more disturbing, called gravitational time dilation, where time runs slower in stronger gravitational fields. So if you were watching a friend fall toward a black hole from a safe distance, you'd never actually see them cross the event horizon. Instead, they'd appear to slow down asymptotically, their image freezing and redshifting toward invisibility as the light they emit becomes increasingly stretched and weakened, taking longer and longer to climb out of the deepening gravitational well to reach your eyes. While from your friend's perspective, they'd cross the horizon in finite time and meet their doom within seconds or minutes depending on the black hole's size, experiencing the universe outside the black hole, speeding up dramatically, watching stars burn out and galaxies evolve in fast forward as they plunge toward the singularity. The differences between black hole masses create wildly different experiences. Stellar mass black holes, formed from individual star collapses, and typically ranging from 5 to a few dozen solar masses, have event horizons only tens of kilometers across, and the tidal forces near their horizons are apocalyptic. The gravitational pull on your feet would be exponentially stronger than on your head if you fell in feet first, a process gruesomely nicknamed spaghettification, where you'd be stretched into a thin strand of atoms long before crossing the horizon. But supermassive black holes like Sagittarius A star, with millions to billions of solar masses, have event horizons measured in millions of kilometers, and because the gravitational gradient is much gentler across that vast distance, you could theoretically cross the horizon without immediately being torn apart, floating serenely into the black hole's interior before the crushing singularity at the center eventually destroyed you. Black holes also come in different flavors depending on their rotation and charge. The simplest type is a Schwarzschild black hole, which is non-rotating and uncharged, described by the first exact solution to Einstein's field equations found by Carl Schwarzschild in 1916, while he was serving in the German army during World War I. Remarkably, he solved these equations in the trenches and sent his results to Einstein, who was stunned that someone found an exact solution so quickly. But Schwarzschild died from an illness just months later, never seeing the full impact of his discovery. Most real black holes aren't stationary. They're rotating, sometimes at nearly the speed of light, because they inherit the angular momentum of the collapsing star that formed them, and rotation adds a whole new layer of weirdness through an effect called frame dragging, where the spinning black hole literally drags space-time around with it, like a whirlpool, creating a region called the ergosphere, outside the event horizon, where it's impossible to stand still relative to distant stars, because space-time itself is being pulled around the black hole, forcing you to move with it, even if you're firing rockets in the opposite direction. The mathematics describing rotating black holes, called the Kerr solution, after Roy Kerr, who discovered it in 1960, predicts that extreme rotation could theoretically create a ring-shaped singularity instead of a point, and passing through this ring might, and this is pure speculation, connect to other regions of space-time, or even different universes, though most physicists think quantum effects would prevent such exotic behavior, and we simply don't have a theory of quantum gravity to tell us what really happens at singularities. Black holes also emit radiation, which sounds paradoxical, since nothing can escape them. But in 1974, Stephen Hawking calculated that quantum effects near the event horizon allow black holes to slowly radiate energy in what's now called Hawking radiation. The mechanism involves virtual particle pairs spontaneously forming near the horizon, with one particle falling in while the other escapes. And from the outside, it looks like the black hole is emitting particles and losing mass, meaning black holes aren't truly eternal. They eventually evaporate over timescales so absurdly long that a solar mass black hole would take 10 to the 67 power years to evaporate, vastly longer than the current age of the universe at 13.8 billion years. But tiny primordial black holes from the early universe could be evaporating right now, and astronomers are searching for the gamma-ray bursts that would signal such events. The first observational evidence of black holes came not from seeing them directly, which is impossible, but from watching how they affect their surroundings. In the 1970s, astronomers discovered X-ray binary systems, where visible stars orbit invisible companions that were too massive to be neutron stars and too compact to be anything but black holes, with Cygnus X1 being the most famous example. And more recently, observations of stars orbiting Sagittarius A star, with precise measurements showing their elliptical paths and relativistic speeds, provided ironclad proof that a massive black hole sits at our galaxy's center. The ultimate confirmation came in April 2019, when the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, actually the supermassive black hole at the center of the galaxy, Messier 86, about 55 million light-years away, showing a dark circular region surrounded by a bright ring of glowing accretion disk material. And that shadow's size and shape matched Einstein's predictions with eerie precision, providing visual proof that event horizons are real and gravity really does trap light in the exact way general relativity describes. Black holes don't just trap light and matter. They trap information itself, leading to a paradox that's plagued physicists for decades. Quantum mechanics says information can't be destroyed, but if you throw something with information encoded in it into a black hole, and the black hole eventually evaporates via Hawking radiation, where did that information go? Because the radiation is thermal and appears to carry no information about what fell in And this information paradox has sparked fierce debates, with recent proposals suggesting information might be encoded in subtle correlations in the radiation, or stored at the event horizon in a holographic manner. But there's still no consensus, and resolving this puzzle likely requires a complete theory of quantum gravity that we don't yet possess. Standing near a black hole would subject you to gravitational forces so extreme that they'd warp your perception of the universe. Looking away from the black hole, you'd see a distorted fisheye view of the entire cosmos, compressed into a shrinking circle, as light from all directions bends around the black hole's gravity. While looking toward the black hole, you'd see the event horizon as a perfect black disk surrounded by twisted multiply-imaged stars and galaxies whose light has been bent into wild trajectories. And if the black hole is accreting matter, you'd witness the brilliant light show of the accretion disk, though you'd only have seconds to appreciate it before tidal forces ripped you apart or radiation cooked you. The physics of black holes represents gravity at its most extreme, where space-time curvature becomes so steep that it creates one-way membranes in reality, regions from which no signal, no particle, no information can ever return. And understanding these cosmic extremes pushes the boundaries of physics, forcing us to confront the limits of general relativity and the desperate need for quantum gravity, while also revealing that our universe contains pockets of such concentrated gravitational power that they fundamentally alter the structure of space-time itself, trapping even light in eternal prisons from which not even the fastest speed nature allows can provide escape. Here's the dirty secret physicists don't want you to know. The two most successful theories in the history of science, general relativity and quantum mechanics, are fundamentally incompatible with each other. And when you try to merge them to understand gravity at the smallest scales, the math explodes into nonsensical infinities and paradoxes that make the entire framework collapse. Which is why, after more than a century of trying, we still don't have a working theory of quantum gravity. And this failure represents the biggest crisis in modern physics, a gaping wound in our understanding of reality that refuses to heal. General relativity, Einstein's masterpiece that describes gravity as curved space-time, works flawlessly for massive objects like planets, stars, and black holes, predicting their behavior with breathtaking accuracy across cosmic distances, while quantum mechanics governs the subatomic realm of electrons, photons, and quarks, with probabilistic rules that allow particles to exist in multiple states simultaneously, tunnel through barriers they shouldn't be able to cross, and become entangled across vast distances in ways that Einstein himself called spooky action at a distance. And here's the problem. These two theories use completely different mathematical languages and philosophical frameworks, with relativity treating space-time as a smooth, continuous fabric, and quantum mechanics describing reality as fundamentally grainy and discrete, where energy comes in packets called quanta and measurements collapse wave functions into definite outcomes. And when you try to apply quantum principles to gravity, everything breaks down spectacularly. The clash becomes unavoidable at the Planck scale, named after physicist Max Planck, which represents the frontier where quantum effects and gravitational effects become equally important. The Planck length is about 1.6 times 10 to the negative 35 power meters, which is so absurdly tiny that it's closer to the size of a proton than a proton is to the size of a car. And at this scale, the uncertainty principle of quantum mechanics, which says you can't simultaneously know a particle's exact position and momentum, starts warping space-time so violently that the very concept of a smooth geometric background falls apart, replaced by what physicists call quantum foam, a churning sea of virtual black holes and wormholes, constantly appearing and disappearing in space-time fluctuations too small and too brief to directly observe. Imagine trying to measure the curvature of space-time at these scales. According to Heisenberg's uncertainty principle, Probing smaller distances requires higher energy, and when you pack enough energy into a small enough region, you eventually create a black hole. So there's literally a fundamental limit to how finely you can measure space-time before your measurement apparatus itself collapses into a gravitational singularity. This isn't a technical limitation of our instruments. It's a built-in feature of reality that tells us space-time probably doesn't exist as a smooth continuum, smallest scales, but rather as some kind of discrete quantum structure we don't yet understand. One of the biggest headaches comes from trying to treat gravity as a quantum field like the other fundamental forces, electromagnetism, the strong nuclear force and the weak nuclear force, all have successful quantum field theories, where forces are mediated by exchanged particles, called bosons, photons for electromagnetism, gluons for the strong force, and W and Z bosons for the weak force. So naturally, physicists tried to quantize gravity by proposing a hypothetical particle called the graviton, a massless spin 2 boson that would mediate gravitational attraction, and at low energies, this approach actually works reasonably well, allowing physicists to calculate tiny quantum corrections to Newtonian gravity. But when you push the theory to higher energies, disaster strikes because the calculations start producing infinite answers that can't be eliminated through a process called renormalization, which normally works for other quantum field theories by absorbing infinities into redefined constants. But for quantum gravity, infinitely many types of infinities appear, requiring infinitely many adjustments, which renders the theory useless for making predictions. And this technical failure signals something deeper. Gravity fundamentally doesn't want to be quantized in the same way as other forces. The root of the incompatibility lies in how the two theories treat time and space. In quantum mechanics, time is absolute and universal, flowing steadily forward as a parameter against which events unfold, providing a fixed stage where quantum wave functions evolve according to the Schrödinger equation. But in general relativity, time is relative and dynamical, interwoven with space into space-time, that bends and stretches depending on mass and energy, with different observers experiencing time at different rates, depending on their motion and gravitational environment. So there's no universal clock that all observers agree on, and reconciling these contradictory views of time has proven extraordinarily difficult because quantum mechanics needs a fixed background to operate on, while general relativity makes that background dynamic and observer-dependent. Another mind-bending problem emerges when you consider what quantum superposition means for gravity. In quantum mechanics, a particle can exist in multiple states simultaneously until measured, famously illustrated by Schrödinger's cat being both alive and dead until you open the box. But if you apply this to gravity, you run into absurdities. Imagine a massive object in a quantum superposition of being in two different locations at once, which quantum mechanics says is perfectly allowed. Each location would curve space-time differently, so you'd have space-time itself in a superposition of different geometries. And now ask yourself, if a test particle falls through this region, which geometry does it follow? And how do you even define what following a geodesic means when space-time doesn't have a definite shape until measured, and who or what counts as a measurement in this context? Since gravity affects everything automatically without requiring a conscious observer. These aren't just philosophical puzzles. They're technical obstacles that prevent physicists from writing down consistent equations that respect both quantum mechanics and general relativity. Physicists have proposed several candidate theories to resolve this mess, each with its own strengths, weaknesses, and devoted followers. String theory posits that fundamental particles aren't point-like objects, but rather tiny vibrating strings of energy. And different vibration modes correspond to different particles, including a vibrational pattern that matches the properties of a graviton. And string theory requires extra spatial dimensions beyond the three we experience. typically 6 or 7 additional dimensions curled up so small we can't detect them. And in this framework, space-time emerges from more fundamental string interactions, potentially resolving the conflict. But string theory has been criticized for making few testable predictions and existing in countless possible versions, leading skeptics to question whether it's even science or just elegant mathematics, with no connection to reality. Loop quantum gravity takes a different approach, starting from general relativity itself and attempting to quantize the geometry of space-time directly, rather than treating it as a background field. And this theory predicts that space has a discrete, granular structure at the Planck scale, composed of tiny loops woven together into networks called spin networks that evolve over time. And in this picture, area and volume come in discrete chunks. There's a smallest possible area and a smallest possible volume, making space-time fundamentally digital rather than analog. And loop quantum gravity successfully eliminates the singularities at black hole centers and the Big Bang by preventing infinite curvature, replacing them with quantum bounces or bridges. But the theory struggles to recover ordinary smooth spacetime at larger scales and has difficulty incorporating matter and other forces. Other approaches include causal set theory, which treats spacetime as a collection of discrete points with causal relationships between them, like a network of cause and effect connections, and asymptotic safety, which argues that gravity might be renormalizable. After all, if you look at it the right way at high energies, and emergent gravity theories that suggest spacetime and gravity aren't fundamental, but rather emerge from more basic microscopic degrees of freedom, similar to how temperature and pressure emerge from the statistical behavior of molecules, with some proposals suggesting spacetime as a kind of quantum error correcting code or holographic projection from lower dimensional physics. The experimental challenge is enormous because quantum gravitational effects only become significant at the Planck energy, which is about 10 to the 19th power giga-electron volts. That's a billion times more energetic than anything the Large Hadron Collider can produce. And achieving such energies would require a particle accelerator, the size of the Milky Way galaxy. So direct tests of quantum gravity seem hopelessly out of reach with foreseeable technology. But physicists are clever and have proposed indirect ways to search for quantum gravitational signatures, looking for tiny violations of Lorentz invariance, which is the principle that physics looks the same regardless of your velocity, searching for subtle patterns in the cosmic microwave background radiation left over from the Big Bang that might carry imprints of quantum space-time structure, detecting graviton-induced noise in gravitational wave detectors like LIGO, or measuring whether gravity can entangle quantum particles. Because if gravity is truly quantum, it should be able to create quantum correlations between massive objects. Recently, experiments have started probing the interface between quantum mechanics and gravity in remarkable ways. Physicists in Vienna measured how Earth's rotation affects the quantum phase of entangled photons, demonstrating that gravity influences quantum systems in measurable ways. And other groups are attempting to detect gravitational decoherence, where quantum superpositions might collapse due to interactions with the gravitational field, potentially explaining why we never see macroscopic objects like cats in quantum superpositions. Maybe gravity itself acts as a measurement device that collapses wave functions once objects become massive enough. Though this remains highly speculative and controversial, the stakes couldn't be higher because quantum gravity isn't just about reconciling two theories for aesthetic reasons. It's essential for understanding the most extreme conditions in the universe. What happened in the first 10 to the negative 43 power seconds after the Big Bang, called the Planck epoch, when the universe was so hot and dense that quantum gravitational effects dominated what exists at the singularities inside black holes, where curvature becomes infinite and general relativity breaks down. Whether the Big Bang was truly the beginning of time, or if it was preceded by something else, like a contracting phase that bounced into expansion, and whether information is truly lost when it falls into black holes, or if quantum gravity provides a mechanism for preserving it. The conflict between quantum mechanics and gravity also raises profound philosophical questions about the nature of reality. Is space-time fundamental, or does it emerge from something deeper? Is time real, or is it an illusion, arising from quantum entanglement, as some physicists have suggested? Does the universe exist in a definite state, or does it remain in quantum superposition until observed? And if so, observed by whom, since there's nothing outside the universe to look at it? And why does nature use two completely different mathematical frameworks for different regimes, when we expect a unified description to exist? Some physicists have even suggested that trying to merge quantum mechanics and gravity is the wrong approach. Maybe one or both theories need to be modified or replaced entirely, with general relativity perhaps being wrong at very small scales, and quantum mechanics breaking down in strong gravitational fields, requiring a revolutionary new framework that reduces to both theories in appropriate limits, but looks radically different at the Planck scale. The absence of a quantum theory of gravity creates a gaping hole in our understanding of the universe. We have two spectacularly successful theories that together explain nearly every observed phenomenon, from subatomic particles to galaxy clusters, yet they contradict each other at a fundamental level. And this contradiction isn't just an academic curiosity. It represents a genuine limitation on our ability to understand reality, signaling that something profound is missing from our picture of how nature works. And until we solve this puzzle, we can't claim to truly understand gravity, because we only understand its classical approximation, which breaks down precisely where things get most interesting, at the smallest scales and most extreme conditions, where the quantum and gravitational worlds collide, and our current theories shatter into mathematical chaos, leaving physicists searching desperately for the missing piece that will finally unite these two pillars of modern physics into a single coherent framework that describes how the universe actually works at every scale. Get ready for the most humbling truth in modern science. Everything you can see, touch, measure, or detect with any instrument, every star, planet, galaxy, atom, and particle in the entire observable universe adds up to a pathetic 5% of what's actually out there, which means 95% of the cosmos is made of stuff we can't see, can't touch, and don't understand. And this invisible majority comes in two flavors that physicists have embarrassingly named dark matter and dark energy. Not because we know what they are, but because we literally have no clue and needed placeholder names for the mysterious forces governing the universe's behavior. Dark matter makes up about 27% of the universe's total mass energy content and acts like cosmic glue, holding galaxies together through gravitational attraction, while dark energy comprises a whopping 68% and does the exact opposite, pushing the universe apart with a kind of anti-gravity that's accelerating the expansion of space itself. And the crazy part is, we only discovered these invisible components because the universe wasn't behaving the way our equations said it should, revealing gaping holes in our understanding of gravity's influence across cosmic scales. The story of dark matter begins in 1933, when Swiss astronomer Fritz Zwicky was studying the Coma galaxy cluster, a massive collection of over 1,000 galaxies bound together by gravity, and he measured how fast individual galaxies were moving within the cluster using the Doppler shift of their light, expecting to find velocities consistent with the visible mass holding them together. But instead, he found something shocking. The galaxies were whipping around so fast that the cluster's visible mass could only provide about 1/400th of the gravitational force needed to keep them from flying apart. Meaning, either Newton's and Einstein's gravity laws were completely wrong on large scales, or there was a huge amount of invisible matter providing the extra gravitational pull, and Zwicky called this unseen stuff dark matter. Though his contemporaries largely ignored him for decades, dismissing his calculations as flawed. The evidence became undeniable in the 1970s when astronomer Vera Rubin meticulously measured rotation curves of spiral galaxies, graphs showing how fast stars orbit at different distances from the galactic center. And basic physics says that stars far from the center should orbit more slowly, just like planets farther from the sun move slower in their orbits, because the gravitational pull weakens with distance. But Rubin found that stars at the edges of galaxies were moving just as fast as those closer to the center, completely defying expectations. And the only explanation that made sense was that galaxies are embedded in massive spherical halos of invisible dark matter, extending far beyond the visible disk, providing extra gravitational pull that keeps outer stars moving fast. And subsequent observations of hundreds of galaxies confirmed this pattern universally, forcing astronomers to accept that the glowing stars and gas we see are just the tip of the iceberg, floating in vast oceans of dark matter that outweighs visible matter by about 6 to 1. Dark matter doesn't interact with electromagnetic radiation at all. It doesn't emit, absorb, or reflect light, making it completely invisible to telescopes that detect photons. And it also doesn't interact with the strong or weak nuclear forces that govern atomic nuclei, which means it passes through ordinary matter like a ghost. And the only way dark matter reveals itself is through gravity, bending light, holding galaxies together, and creating the cosmic scaffolding upon which visible structures formed. And physicists have proposed dozens of candidates for what dark matter particles might be, with the leading contender being WIMPs, which stands for weakly interacting massive particles, hypothetical subatomic particles with masses perhaps 10 to 100 times that of a proton that only interact through gravity, and possibly the weak nuclear force, making them extraordinarily difficult to detect directly. Scientists have built ultra-sensitive detectors deep underground, shielded from cosmic rays and background radiation, hoping to catch the extremely rare event of a dark matter particle colliding with an atomic nucleus. And despite decades of searching with increasingly sophisticated experiments like Xenon, Lux, and Super CDMS, they've found nothing conclusive, leading some physicists to consider alternative candidates like axions, which are hypothetical ultralight particles that could permeate space in enormous densities, or primordial black holes, which are tiny black holes that might have formed in the early universe and now constitute dark matter halos. Though each candidate has theoretical challenges and none have been confirmed. Meanwhile, dark energy presents an even deeper mystery, because while dark matter at least behaves like normal matter gravitationally, just invisible, dark energy does something that seems to violate common sense. It exerts a repulsive gravitational effect that pushes things apart, and this bizarre property was discovered in 1998 when two independent teams of astronomers studying distant Type 1a supernovae, which are exploding white dwarf stars that serve as cosmic distance markers because they all have nearly the same intrinsic brightness, expected to find that the universe's expansion was gradually slowing down due to the attractive pull of all the matter in the cosmos. But instead, they found the exact opposite. The expansion was speeding up, accelerating over time, as if something was actively pushing galaxies away from each other with increasing strength. And this discovery was so shocking and unexpected that both teams checked and rechecked their data for months before publishing, eventually earning the lead scientists the Nobel Prize in Physics in 2011 for overturning our understanding of the universe's fate. Dark energy's repulsive effect only becomes significant over vast cosmic distances, on scales of individual galaxies or galaxy clusters. Ordinary matter and dark matter dominate gravitationally, holding structures together. But when you zoom out to hundreds of millions or billions of light years, dark energy's influence takes over, stretching the fabric of space itself and driving galaxies apart. And here's the really weird part. Dark energy appears to have constant density throughout space, meaning as the universe expands and creates more volume, more dark energy appears to fill that volume. which sounds like it violates energy conservation, until you realize that the expansion of space itself involves negative gravitational potential energy that can balance the creation of dark energy, though this explanation still feels deeply unsatisfying and mysterious. The leading theoretical explanation for dark energy is Einstein's cosmological constant, a term Einstein originally added to his general relativity equations in 1917 to make the universe static, because at the time everyone thought the cosmos was eternal and unchanging. But when Edwin Hubble discovered the universe was expanding in 1929, Einstein reportedly called the cosmological constant his biggest blunder and removed it. Yet physicists have resurrected this concept to explain dark energy as the intrinsic energy of empty space itself, called vacuum energy, arising from quantum fluctuations where virtual particle pairs constantly pop in and out of existence throughout the vacuum. And quantum field theory predicts this should create an energy density pervading all of space. But here's the catastrophic problem. When physicists calculate how much vacuum energy there should be, based on quantum mechanics, they get an answer that's 10 to the power of 120 times larger than the observed value, which is literally the worst prediction in the history of physics, off by a factor with 120 zeros. And nobody understands why the actual dark energy density is so extraordinarily tiny compared to theoretical expectations, making this the deepest unsolved problem at the intersection of quantum mechanics and gravity. An alternative theory called quintessence proposes that dark energy isn't a constant property of space, but rather a dynamic field pervading the universe, similar to other quantum fields, like the electromagnetic field, and this quintessence field would have negative pressure causing repulsive gravity. And unlike the cosmological constant, which stays perfectly uniform, quintessence could evolve over time, potentially explaining why dark energy only started dominating the universe's expansion about 5 billion years ago, after matter and dark matter had enough time to clump into galaxies and clusters. Though quintessence theories face their own challenges and haven't been conclusively tested, some radical physicists have suggested that instead of inventing dark matter and dark energy, maybe our understanding of gravity itself is wrong at cosmic scales, leading to modified theories like MONDAT, which stands for Modified Newtonian Dynamics, proposing that gravity behaves differently when accelerations become extremely small, as in the outer regions of galaxies, eliminating the need for dark matter, or theories suggesting that general relativity breaks down over cosmological distances, removing the need for dark energy. But these alternative gravity theories struggle to explain the full range of observations as successfully as the standard dark matter plus dark energy model, particularly detailed measurements of the cosmic microwave background radiation, which is the afterglow of the Big Bang, and carries imprints of how matter was distributed in the early universe. And the patterns in this radiation match predictions from models with dark matter, but not from modified gravity theories. The cosmic microwave background provides some of the strongest evidence that dark matter is real. In the infant universe, about 380,000 years after the Big Bang, ordinary matter and radiation were tightly coupled, bouncing off each other and creating pressure waves called baryon acoustic oscillations, which are essentially sound waves traveling through the primordial plasma. But dark matter, which doesn't interact with radiation, wasn't affected by this pressure and started clumping together gravitationally much earlier, creating gravitational wells that ordinary matter eventually fell into after the universe cooled enough for atoms to form and radiation to decouple. And this head start in structure formation is crucial because computer simulations show that without dark matter, there wouldn't have been enough time for gravity to pull ordinary matter together into the galaxies and large-scale structures we see today. The universe is only 13.8 billion years old, and gravity working on visible matter alone is too slow to build the cosmic web of galaxy filaments and clusters observed across the sky. Gravitational lensing provides another stunning confirmation of dark matter's existence. Einstein's general relativity predicts that mass bends spacetime and deflects light, passing nearby. So when light from distant galaxies travels through the gravitational field of a massive galaxy cluster in the foreground, the light gets bent and distorted, creating multiple images or arcs of the background galaxies. And by carefully analyzing these distortions, astronomers can map out where the mass is in the foreground cluster. And repeatedly, these maps show that most of the mass is invisible, concentrated in halos that don't correspond to bright stars or gas. And in dramatic cases, like the Bullet cluster, where two galaxy clusters collided and passed through each other, the hot gas was slowed by electromagnetic interactions and separated from the galaxies, while the dark matter halos passed right through each other unimpeded and carried the galaxies with them, creating a situation where most of the mass, as measured by gravitational lensing, is offset from most of the visible matter in the form of hot gas, providing direct visual evidence that dark matter is distinct from ordinary matter. The implications of dark matter and dark energy are profound and unsettling. They tell us that the atoms making up our bodies, the Earth, the Sun, and all the stars we can see are cosmically irrelevant, just a tiny fraction of the universe's content, and the forces shaping the cosmos on the largest scales are completely invisible and poorly understood, operating through mechanisms we can't directly observe and can only infer from their gravitational effects. And the future of the universe depends entirely on these dark components. If dark energy continues accelerating the expansion, eventually galaxies outside our local group will recede faster than light and disappear beyond a cosmic horizon, leaving future civilizations trillions of years from now in a cold, dark, isolated island universe with no evidence that other galaxies ever existed. But if dark energy weakens or reverses, gravity might eventually win and pull everything back together in a big crunch. Or perhaps dark energy will strengthen and tear apart galaxies, stars, planets, and eventually atoms themselves in a big rip scenario, where the fabric of space expands so violently that it overcomes all forces holding matter together. Current cosmological models describe the universe's composition as about 68% dark energy, 27% dark matter, and 5% ordinary matter, including all the atoms, stars, and galaxies we can see, with tiny fractions coming from photons and neutrinos. And this model, called lambda CDM, where lambda represents the cosmological constant for dark energy, and CDM stands for cold, dark matter, fits observational data extraordinarily well, explaining the cosmic microwave background patterns, galaxy distributions, supernova distances, and structure formation with impressive accuracy. Yet it rests on two enormous unknowns, dark matter and dark energy, that we've labeled and incorporated into equations without truly understanding what they are, which is both a testament to the power of observational astronomy to detect phenomena beyond our immediate comprehension, and a humbling reminder that despite centuries of scientific progress, we remain profoundly ignorant about the fundamental nature of most of the universe, with gravity's hidden influences shaping cosmic evolution through mechanisms we're still desperately trying to uncover. You think gravity is just that mundane force keeping your coffee in the cup and your feet on the floor, but it's secretly messing with your body, warping your experience of time, and influencing every single moment of your existence in ways you've never noticed. And once you understand these hidden effects, you'll never look at standing, walking, or even aging the same way again. Let's start with something that sounds ridiculous, but is absolutely true. You are taller in the morning than you are at night. And we're not talking about a negligible difference. The average person loses between half an inch to 3/4 of an inch in height over the course of a single day, which is about 1 to 2 centimeters. And this daily shrinking act happens because gravity is constantly compressing your spine throughout the day as you stand, walk, and sit, squeezing the fluid-filled discs between your vertebrae. like water being wrung from a sponge. And when you finally lie down to sleep, removing the gravitational load, those disks gradually rehydrate and expand, restoring your full height by morning, which means every single day of your life, you're engaged in this rhythmic dance of compression and expansion. Driven entirely by Earth's gravitational pull, your heart has to work harder because of gravity, pumping blood upward against gravitational force to supply your brain with oxygen, which is why blood pressure is measured in millimeters of mercury, a unit that literally represents the height of a mercury column. Your heart's pressure can support against gravity, and this constant battle against gravity is why astronauts in space experience cardiovascular deconditioning, because in microgravity, their hearts don't have to work as hard to circulate blood, so the muscles weaken over time. And when they return to Earth, they often experience dizziness and fainting until their cardiovascular systems readjust to fighting gravity again. Even your sense of up and down is a gravitational illusion created by your vestibular system. In your inner ear, which contains tiny calcium carbonate crystals called otoliths, suspended in fluid, and gravity pulls these crystals downward, causing them to press against sensory hair cells that send signals to your brain about which way is down, so your entire spatial orientation and balance depend on detecting gravity's pull. And when these crystals get dislodged and drift into the wrong canals, you get benign paroxysmal positional vertigo, a condition where sudden head movements trigger intense spinning sensations. Because gravity is moving the crystals in ways that confuse your brain about your actual position. Gravity affects your blood circulation so profoundly that when you stand up quickly after lying down, gravity pulls blood toward your legs, temporarily reducing blood flow to your brain, causing that lightheaded feeling called orthostatic hypotension. And your body has developed sophisticated mechanisms to counteract this, including the immediate constriction of blood vessels in your legs and abdomen, and a slight increase in heart rate within seconds of standing. But sometimes these compensations aren't fast enough, which is why people occasionally faint when standing up too quickly, especially if they're dehydrated or have cardiovascular issues. Time itself runs differently at your head than at your feet because of gravitational time dilation. And this isn't science fiction, it's a measured reality, confirmed by ultra-precise atomic clocks that show time moves faster at higher altitudes, where gravity is slightly weaker, meaning your head is literally aging faster than your feet by about 90 billionths of a second over a 70-year lifetime, which sounds trivial, but demonstrates that every part of your body exists in a slightly different time frame, depending on its height in Earth's gravitational field. And while this difference is negligible for humans, it's absolutely crucial for technologies like GPS satellites, which orbit about 12,500 miles above Earth, where gravity is weaker and time runs faster by about 38 microseconds per day, compared to clocks on the ground. And if engineers didn't correct for this relativistic time dilation, GPS navigation would drift by about 6 miles per day, rendering the system useless. Your bones are actively being remodeled every single day in response to gravity's constant stress, with osteoblast cells building new bone tissue where mechanical stress is detected, and osteoclast cells breaking down bone in areas that aren't being stressed, which is why weight-bearing exercise is crucial for maintaining bone density. Your skeleton literally needs gravity's compression to stay strong, and this becomes tragically obvious in astronauts who lose 1 to 2% of their bone mass per month in space, despite rigorous exercise routines, because without gravity providing constant mechanical loading, their bodies interpret the lack of stress as a signal that bones are overbuilt and start dismantling them to save resources. And returning astronauts can take months or even years to fully recover lost bone density, if they ever do. Gravity is constantly trying to pull your body downward, and your muscles are constantly fighting back, burning energy just to keep you upright and maintain posture which is why standing still actually burns more calories than lying down. Your leg muscles, back muscles, and core are all working continuously to counteract gravitational collapse. And this is why you feel tired after standing for long periods, even if you haven't actively moved, because your muscles have been engaged in sustained isometric contraction against gravity's relentless pull. The shape of your body itself is sculpted by gravity. Your internal organs are suspended and positioned by connective tissues that evolved to function under Earth's gravitational field, with structures like ligaments holding your liver, stomach, and intestines in place against the downward pull. And in the absence of gravity, as astronauts have discovered, organs shift position, fluids redistribute throughout the body, causing facial puffiness and leg thinning. And digestive processes change because food doesn't settle naturally in the stomach, requiring peristalsis, muscular contractions to push everything through the digestive tract instead of gravity, helping move things along. Every time you lift something, you're fighting against gravity, and the energy you expend is directly proportional to the object's mass times the gravitational acceleration times the height you lift it, which is why carrying a heavy backpack up a mountain is exponentially more exhausting than carrying it on flat ground. You're not just moving the mass horizontally, but also lifting it against gravity's pull with every step upward, converting your metabolic energy into gravitational potential energy stored in the elevated mass. Your blood vessels have evolved specialized valves in your legs that prevent blood from flowing backward when gravity pulls it downward. And these one-way valves are crucial for returning blood to your heart from your lower extremities. But when these valves fail or weaken, blood pools in the legs, causing varicose veins, where the veins become swollen and twisted from accumulated blood fighting a losing battle against gravity. And this condition affects millions of people, especially those who stand for long periods, because gravity has literally decades to exploit any weakness in your circulatory system's return mechanism. The simple act of breathing is influenced by gravity because it pulls your lungs downward, creating pressure gradients that cause more air to flow to the bottom portions of your lungs when you're upright, meaning the lower lobes receive more ventilation and blood flow than the upper lobes due to gravitational effects. And this is why lung function tests show different results depending on whether you're standing, sitting, or lying down. And astronauts in microgravity experience changes in respiratory patterns, because without gravity creating these pressure gradients, air distributes more evenly throughout the lungs, changing gas exchange efficiency. Gravity even affects how fast wounds heal, because it influences blood flow to damaged tissues. And studies have shown that healing can be impaired in microgravity environments because the normal inflammatory response and delivery of immune cells depends partially on gravity-driven blood circulation patterns, though the mechanisms are still being researched. And this has serious implications for long-duration space missions, where injuries might heal more slowly or differently than on Earth. Your eyes are affected by gravity too. The shape of your eyeball is partially maintained by internal fluid pressure, balanced against external atmospheric pressure, and the structural integrity provided by tissues that shew under constant gravitational loading. And in microgravity, some astronauts develop vision problems called spaceflight-associated neuroocular syndrome, where increased intracranial pressure pushes on the back of the eyeball, flattening it slightly and causing changes in vision that can persist after returning to Earth. And scientists are still trying to understand all the mechanisms involved, but it's clear that removing gravity from the equation disrupts the delicate balance of forces shaping our eyes. The water in your body, which makes up about 60% of your mass, is constantly being pulled downward by gravity, creating hydrostatic pressure that's higher in your feet than in your head when you're upright. And this pressure gradient is why your feet and ankles can swell after standing all day. The increased pressure in lower extremities causes fluid to leak from blood vessels into surrounding tissues, creating edema. And when you elevate your legs or lie down, reducing the gravitational gradient, the fluid gradually returns to circulation, and the swelling goes down. Gravity determines how substances separate. In your blood, when you spin samples in a centrifuge, with denser components like red blood cells settling to the bottom and lighter plasma rising to the top, mimicking an enhanced gravitational field that accelerates the natural settling process that would eventually occur under normal gravity. Given enough time, and this separation by density is fundamental to countless medical tests and procedures that depend on gravity's ability to sort materials by mass. Even your sense of taste might be affected by gravity. Astronauts frequently report that food tastes bland in space, and while some of this is due to fluid redistribution, causing nasal congestion, researchers suspect that the absence of gravity might also affect how taste molecules move in saliva and interact with taste receptors on the tongue. Though this remains an active area of investigation, but it demonstrates that even something as seemingly unrelated as flavor perception might have subtle gravitational dependencies we never noticed, because we've always experienced taste under Earth's gravity. The way you walk is an elegant dance with gravity, where you're essentially controlled falling. Each step involves leaning forward and letting gravity pull you into a fall, then catching yourself with your opposite leg before hitting the ground. And the energy efficiency of human walking depends critically on this gravitational pendulum motion, where your center of mass rises and falls with each stride, converting kinetic energy to gravitational potential energy and back, minimizing the muscular work required. And this is why walking on the moon, with only 1/6 Earth gravity, required astronauts to adopt a bouncing gait. The normal walking motion didn't work efficiently in the reduced gravitational field. Gravity creates a pressure gradient in the atmosphere that makes air denser at sea level and thinner at higher altitudes, which directly affects how much oxygen you can breathe. The air at the summit of Mount Everest, which is about 5.5 miles high, has only about 1/3 the oxygen concentration of sea level air. Not because oxygen percentage changes, but because the overall air pressure is lower due to less gravitational compression, making every breath deliver less oxygen to your lungs. And this is why climbers need supplemental oxygen or extensive acclimatization to survive at extreme altitudes where gravity's grip on the atmosphere weakens. Your aging process itself might be influenced by gravity's constant mechanical stress on your body. Some researchers hypothesize that the cumulative damage from a lifetime of gravitational loading contributes to the deterioration of joints, the compression of the spine, the sagging of skin and soft tissues, and even potentially to cellular aging through mechanical stress pathways. Though teasing apart gravity's role from other aging factors is incredibly difficult, but it's fascinating to consider that the very force keeping you anchored to Earth might also be gradually wearing down your body over decades of constant compression. Every single breath, heartbeat, step, and movement you make is choreographed in an intricate dance with gravity that you never consciously notice because it's been the constant background rhythm of your entire existence. But understanding these hidden influences reveals that you're not just living on Earth. You're living in an intimate, inescapable partnership with gravity that shapes your body, influences your health, warps your time, structures every moment of your physical experience in ways both profound and invisible. And recognizing this cosmic relationship transforms the mundane act of simply standing upright into a testament to your body's remarkable adaptations to survive and thrive under the relentless, ever-present pull of the planet beneath your feet. So here we are at the end of this journey through gravity's twisted mysteries. And if you thought we'd wrapped everything up with a neat bow and a satisfying explanation, think again. The truth is that despite centuries of brilliant minds attacking the problem, despite Newton's equations and Einstein's geometric revolution, despite billion-dollar particle accelerators and gravitational wave detectors, listening to spacetime's vibrations, we still don't truly understand what gravity is, why it exists, or how it fits into the deeper fabric of reality. And that admission should simultaneously terrify and excite you, because it means we're living in an era where one of the universe's most fundamental forces remains profoundly mysterious, hiding secrets that could unlock entirely new physics and reshape our understanding of existence itself. Think about the absurdity of our situation. We can predict planetary orbits centuries in advance with breathtaking precision. We've detected gravitational waves from black holes colliding a billion light-years away. We've photographed the shadow of a supermassive black hole 55 million light-years distant. Yet we can't reconcile gravity with quantum mechanics. Can't detect the hypothetical graviton particle that supposedly mediates gravitational force. Can't explain why gravity is 10 to the 39 power times weaker than electromagnetism. A disparity so enormous, it's called the hierarchy problem, and has no satisfactory explanation, and can't figure out what 95% of the universe is made of, because dark matter and dark energy remain complete enigmas whose existence we infer only from their gravitational effects, meaning our supposed mastery of gravity is built on a foundation of cosmic ignorance that should humble every physicist on the planet. The quest for quantum gravity has consumed generations of brilliant theorists who've constructed elaborate mathematical frameworks like string theory, with its requirement for 10 or 11 dimensions, most of which are supposedly curled up so tightly we can't detect them, or loop quantum gravity, with its prediction that space-time is fundamentally granular and discrete at the smallest scales. Yet neither approach has produced a single testable prediction that could be verified with current technology, leaving physicists arguing over mathematical elegance and philosophical preferences, rather than experimental evidence, which is basically unheard of in a field that prides itself on empirical verification. And this theoretical deadlock has lasted for decades with no resolution in sight, suggesting that maybe we're missing something fundamental about how nature works at the intersection of gravity and quantum mechanics. Consider the philosophical implications of what we've discovered about gravity. If Einstein is right, and gravity is just curved space-time, then what is space-time made of, and does it even exist at the Planck scale, where quantum fluctuations supposedly tear the smooth fabric into a foaming chaos of virtual particles and micro-wormholes? And if space-time is emergent, arising from more fundamental quantum information, or entanglement as some cutting-edge theories suggest, then what does that mean for our concepts of distance, duration, causality, and the very notion of physical reality? Because if the stage upon which all events unfold is itself a derived quantity rather than a fundamental feature of the universe, we might need to completely rethink the relationship between matter, energy, information, and the geometric arena we call space-time. The cosmic mysteries pile up in ways that should shake your confidence in humanity's understanding of the universe. Why did the Big Bang happen? And what, if anything, existed before it? What truly occurs at the singularity inside a black hole, where our equations break down and produce infinite curvature and density? Does information that falls into a black hole get destroyed, violating quantum mechanics' sacred principle of information conservation? Or is it somehow encoded on the event horizon, or released in Hawking radiation through mechanisms we don't understand? Why is dark energy's measured value so absurdly smaller than quantum field theory predicts it should be, creating the worst theoretical prediction in physics history, with a discrepancy of 120 orders of magnitude? And why does the universe appear so precisely fine-tuned for life, with the strength of gravity and other forces falling within the incredibly narrow ranges needed for stars to form, heavy elements to be created, and planets to exist? When if gravity were even slightly stronger or weaker, the cosmos would be either a collection of black holes or a diffuse cloud of hydrogen, with no structure at all. Some physicists have proposed that we live in a multiverse, with countless bubble universes, each with different physical constants and force strengths, and we just happen to find The fact that gravity behaves so differently from the other fundamental forces should bother you. Electromagnetism, the strong nuclear force, and the weak nuclear force all fit beautifully into the standard model of particle physics, with their force carrier particles and quantum field descriptions. But gravity stands apart, refusing to be quantized in the same way, operating by seemingly different rules that involve the geometry of space-time rather than particle exchanges. And this stubborn uniqueness suggests either that gravity is fundamentally different in nature from the other forces, requiring a completely separate theoretical framework, or that we're misunderstanding something basic about how forces work, and there's a deeper unification waiting to be discovered that treats all forces, including gravity, as manifestations of a single underlying principle that we haven't yet glimpsed. Recent experimental hints are making things even more interesting and confusing. Measurements of the universe's expansion rate, using different methods, are giving inconsistent results in what's called the Hubble tension, suggesting either that our measurements have subtle errors we haven't identified, or that our cosmological models are missing crucial physics, possibly related to how dark energy behaves or evolves over cosmic time. Observations of galaxy rotation curves and gravitational lensing continue to demand dark matter's existence. If Einstein's general relativity is correct, yet decades of increasingly sensitive searches have failed to detect dark matter particles directly, leading some physicists to wonder if we need to modify gravity itself at galactic scales through theories like modified Newtonian dynamics. Though Mond struggles to explain other observations that dark matter handles easily, leaving us in an uncomfortable position where neither explanation feels fully satisfying. The tools we're developing to probe gravity's mysteries are becoming increasingly sophisticated and bizarre. Physicists are proposing to use quantum entanglement to test whether gravity can create quantum correlations between massive objects, which would prove gravity has quantum properties even if we can't detect individual gravitons. Astronomers are planning next-generation gravitational wave detectors, sensitive enough to potentially observe the stochastic background of gravitational waves from the early universe, which might carry imprints of quantum gravitational effects from the Planck epoch. And theorists are exploring connections between gravity and quantum information theory, discovering mysterious mathematical relationships, suggesting that space-time geometry might be deeply connected to quantum entanglement entropy in ways that could revolutionize our understanding of both fields, with some researchers going so far as to propose that space is quantum entanglement and gravity emerges from the way quantum information is distributed across the universe. The possibility that we might be completely wrong about gravity's fundamental nature should excite you, because scientific revolutions happen when cherished assumptions get overturned, just as Einstein shattered Newton's comfortable universe by revealing that space and time are flexible, intertwined rather than absolute and separate. Perhaps the next revolution will show that space-time itself is an illusion, a holographic projection from a lower dimensional reality, as suggested by the holographic principle, or that gravity doesn't exist as a fundamental force at all, but emerges from the statistical behavior of more basic quantum degrees of freedom, similar to how temperature and pressure emerge from molecular motion. And if this emergent gravity idea is correct, it would completely recontextualize every gravitational phenomenon we've discussed, from falling apples to black holes to the expansion of the universe, revealing them all as macroscopic consequences of microscopic quantum physics we haven't yet properly understood. What keeps physicists awake at night is the nagging suspicion that the key to understanding gravity might require abandoning concepts we consider absolutely fundamental. Maybe the continuous nature of space-time is wrong, and reality is fundamentally discrete and pixelated at the Planck scale. Maybe time isn't a fundamental feature of the universe, but rather emerges from quantum entanglement, correlations. Maybe there's no unified space-time at all, just separate quantum subsystems interacting through gravitational relationships. Maybe gravity isn't even a force in the traditional sense, but rather the geometry of possibility space in quantum mechanics. Or maybe we need to accept that observers and measurements play a fundamental role in physics at all scales, not just in quantum mechanics, with consciousness or decoherence processes somehow involved in how space-time acquires its classical geometric properties, which would be philosophically radical, but might be what the universe is trying to tell us through the persistent incompatibility between quantum mechanics and general relativity. Future experiments and observations will either validate our current frameworks or blow them apart. The James Webb Space Telescope and next-generation observatories are probing the early universe when the first galaxies formed, testing whether dark matter and dark energy models accurately predict structure formation. Particle physics experiments continue searching for supersymmetry, extra dimensions, or new forces that might explain the hierarchy problem and why gravity is so weak. Gravitational wave astronomy is entering a golden age, with multiple detectors online and more being built, promising to reveal colliding black holes, neutron stars, and potentially exotic objects we haven't even imagined. And tabletop quantum experiments are reaching sensitivities where they might detect gravitational effects on quantum superpositions, testing the interface between the quantum and gravitational realms with increasing precision, any of which could yield the unexpected result or anomalous measurement that cracks open our understanding and points toward the next paradigm shift. The most profound realization you should take from this exploration of gravity is that the universe we inhabit is stranger, deeper, and more mysterious than our ancestors could have possibly imagined. And despite all our technological sophistication and mathematical prowess, we're still fumbling in the dark when it comes to understanding the fundamental force that shapes cosmic structure, determines the evolution of the universe, governs the motion of everything from galaxies to atoms, warps the flow of time itself, and might even be telling us that space and time aren't real in the way we intuitively experience them, but are instead emergent phenomena arising from quantum information processing, happening at the deepest levels of reality. And if that doesn't fill you with a sense of wonder and intellectual vertigo, then you haven't truly grasped how little we know and how much remains to be discovered about this force we call gravity, that's been hiding in plain sight throughout human history, pulling at every atom in your body every second of every day, while keeping its deepest secrets locked away behind mathematical barriers and energy scales we can't yet reach, waiting for the next Einstein or Hawking to arrive with the revolutionary insight that finally cracks the code and reveals what gravity actually is, how it truly works, and what role it plays in the ultimate nature of reality. A discovery that, when it comes, and it will come, will transform not just physics, but our entire conception of existence, consciousness, and our place in this vast, gravity-woven cosmos that's far more bizarre and beautiful than we currently comprehend.